Professor,
Yeah.
I was a little confused about so in the assignment for the last question we were supposed to uh, count in two ways for the two questions that were given, and I was really not sure about what possible other way could we approach for counting those things. So one was the handshake lemma, and the other was degree or sum of degrees in a graph is twice the number of edges. So one of the argument for each is pretty simple, but I couldn't figure out what other kind of argument we could use.
Well, so counting in two different ways means something, and that's when I said counting in two different ways. So let me comment on this. So when one says counting in two different ways, this we covered on the first day of class. We mean that we count something like this. So fix. So we count two sets x by x times y, which is ordered pairs like this, and we fix a, count b, and fix b, count a. And basically, when you fix a, count b, then you have some kind of a number like this, in a belonging to x, and then something here for a fixed a, however many b's are there. And when you fix b and count a, you get something like this. Sorry, a belongs to x and some number. And since these two are equal, that means counting in two different ways. So basically, the point of this exercise was, I mean, the exercise was very simple, but the point of the exercise was how to write it in this format. So if you're, what are the pairs you're counting? So you're counting, let's say, um, so what was it? Degrees, right?
Yes, Professor.
This is what you were doing, right?
Yes, Professor.
So what you're counting is you're counting edges. So this is the critical thing. So yeah, I mean, if you're given a graph, so you count pairs of vertex and edges, I think, in two different ways. So if you fix a vertex, then this is the number of edges in one. So fixed v, and you fix e, then there are two edges, and these two are equal. So uh, this is 2 times e, and this is summation bi. Okay, does that explain what I want?
Yes, Professor.
So this was, I mean, we started with this, but we didn't do anything. That's why I needed to put something there. If you remember the first lecture, this is what it is.
Yes, Professor.
I mean, every time there is a sort of, unclear argument uh, in combinatorics, then I usually make this very formal so that I can understand what's going on. Okay, any other questions before we begin? So the plan is to continue with graph theory now that we've started it. Um, so overall, I think when is your so there's just one more week before your midterm break, right? Is that right?
Yeah, I think next week is the last.
Yeah. So the plan was to do half a sem, um, sort of survey of elementary combinatorics, whatever we can manage. So that will continue till end of next week. And then after the break, we'll do a get into partitions. So I'm still right now. Now that we started graph theory, there are a couple of theorems I want to do maybe today and tomorrow, and then there may be a few more things before we get back into. Then we get serious about partition. So partitions and then plus number theory, some little bit of number theory. So I mean they're related. So whatever we are doing is going to be related, and some combinatorial theorems will fall out of the way in the way. So it's not that we are going away from combinatorics or anything of that sort. So okay, so continue. Let's recall uh, Latin squares you were doing, right? By the way, yesterday Bhatia mentioned in his talk that he has used Hall's theorem for a very nice theorem on roots of polynomials and so on. So, but he was unable to switch on his voice, so he gave that comment towards the end, at the end when everybody had left. So he mentioned to Nishad and me that he had earlier used Hall's theorem. So whatever we just did, it was quite useful to him. So it's a very central theorem. Anyway, recall that uh, so an M cross N Latin rectangle uh, is an M cross N matrix such that uh, so this matrix is M equal to Mij uh, with entries from 1 to n such that uh, all the numbers are between 1 and n. Two, no two entries in a row or column are the same. And the theorem is
Mij is from 1 to n. Is
1
that
to n.
n?
Yeah, this is
What?
n. Yeah.
I see.
Professor,
Yeah.
for this we kind of need to have m is less than n, right? Less than or equal to.
Yeah. Yeah. So, yeah. So I wonder, do these nibs have to be changed, or they don't wear down, right? Anyway, so the theorem is let M be an M cross N Latin rectangle, then it can be extended to an N cross N Latin square. So by the addition of certain rows, n minus n rows. So we show using Hall's theorem uh, that one more row can be added. So let m be less than n. So we show one more row can be added, and the proof idea is as follows: let ai be the elements in in uh, such that a is not equal to mij. So elements in a column for fixed I, for fixed j, for I equal to 1 to m. So we have some kind of a, m rows have been fixed. So I equal to 1 up till m are fixed. And we have to fill these guys, and this potential set of numbers which we can fill. So all the numbers, so this is, so aj, so this aj is all the numbers not in column so far. So these are the numbers in the jth column that have not appeared so far in rows 1 to I. So these are the potential candidates for putting it over here. And the idea is we need to show an SDR exists. And once an SDR exists, we just place A1, A2, A3, whatever over here, and then we are done. So how do you show that ADR exists? We need to show that any k of these AJs have um, at least k distinct elements, right? So then only we will be able to do that. So, but each uh, show that the union of any, but any such union has how many elements? So each of them have n minus k elements. Sorry, n minus m elements. So the union will have n minus m times k elements, and these are counted with repetition, right? And if the union has less than, I don't know what is wrong with the writing. if the union of this union of k elements has less than k elements, right? Then what does that mean? Then some uh,
Then some AI must have occurred twice in one column in one of the above M rows.
say that again.
If the union has less than k elements, then in one of the first m rows, some AI must have occurred twice in the same column.
Yeah. So I mean, right. Then some. I'm wondering what to call it. Some number must have appeared more than n minus 1 times above, which is a contradiction. So this is a contradiction because each number comes exactly m times in uh, in the first r rows, first row, in the n rows. So this can't happen, and that means that one can find uh, this thing. So by Hall's theorem, uh,
So, Professor, could you just go over that last part again?
yeah. So um, I mean, let's just do an example. So you have something like this, and then I'm adding uh, what are the possibilities here? Uh, 2, 3, 4, and I'm just adding to this row. And this is 1, 3, 4, and this is 1, 2, 4, and 1, 2, 3. So what he's saying is that if you take any of these guys, let's say we take these guys, then the total number will be n minus. So this is m. This is n minus m. So n minus m times k rows. That means these are two rows. K is 2, n minus m is 3. So counting repetition, right? So you're counting repetition, and they're overall going to be about 6 candidates. Now, if any of the case, so what we want to show is that each number comes at most, must have appeared more than, if there is some number which has, I mean, we want to show that there are at least two numbers here in this case. If it's not the case, then some number must have appeared 3 times. That's what he's saying. And that can't happen because over here it's not come more than it. So you can't if you take if you take the union of this, the union has to be bigger than equal to 2, because otherwise one of the numbers has to come at least 3 times, and that's a problem over here. So then there's a problem in these rows actually. It comes 3 times. That's the problem. I don't know if I can explain it. Just
I'm
think
still a
about
little
it.
confused.
Huh?
Still a little confused. I don't get how we
Well, just
how it's
think about it.
directly.
Huh?
Yeah.
So my suggestion is just think about it. This is something which is sort of hard to explain. It's almost obvious.
Uh,
So let's follow this guy. So So the union has less than, suppose the union has less than k elements, right? So all these rows, so these k rows, um, they have less than k elements here, right? So all these rows is less than k elements. So in one row, some element has to repeat. Suppose in this 1, 2, 3, 4, 5 has less than k, it has only 4 elements. 1, 2, 3, and 4. So there must be some repetition here, right? That is what the problem is. So if these, because over here then, well, okay, think about it. I don't know how to explain this. Ayush, you want to try? Well, it seems to be clear to you.
I mean, it seems sort of intuitive, but I don't get how we directly related those two statements.
Um,
But I'll look at it later.
let's look at it later. I'm a little confused myself about how to explain it. It seems kind of obvious to me that if all of them, I mean, there are k times n minus one in these rows. So I don't know. Let me try again. So with the, let's do a smaller problem. So this is 2, 3. This is 1, 3. This is 1, 2. So this is m, our m, and this is n. Now what what this statement says is we need to show that the union of any k of these, let's say this is the union, so k is equal to 2, has at least k distinct elements. So now this has got, how many elements does it have? It has 4 elements, counting repetitions. So 2 from coming from k and 2 coming from n minus n, right? And he's saying if the union has less than k elements, so if all of these have less than k elements, right? And then whatever, well, this is a bad example because there's just 2, both are the same. Let's do a bigger example. So 1, 2, 3, 4, and 2, 1, 4, 3. Let's say this, okay. So 3, 4, 3, 4, 1, 2, 1. Right? And let's take, so this is, so m is 2, n is 4. And let's take k equal to 3. So let's take these 3 guys. We want to show that the union, we want to show that the union of these 3 guys has to be bigger than 3. So how many total he's saying is n minus m, which is 2 times 3, so there are total 6 elements, counting repetitions, right? Now if he's saying, suppose the union has two elements, right? Suppose the union has just 2 elements. Then some one. So let's say the elements are 3 and 4. So this is the problem. If the union has less than two elements, then some number must have appeared more than n minus 1 times. So some number, in this case 3, has appeared more than 2 times. That is also fair. And that's a problem with over here, because that number can only appear m times here. So this 3, if it has come n minus m times, uh, so it has come more than n minus m times, then there's a problem over here. It can't come over here. So if it has come 3 times, then it couldn't have come here. That is the problem. That's what he's trying to say.
Okay, okay. I think I got it.
I mean, it's in the other part is where the contradiction happens, because that number comes exactly n
Right.
times here. So it has to come exactly n minus m times here. I mean, essentially, it's trying to say that this is less than equal to this and bigger than equal to n minus mk, because each number has come m times already, so it has to come at least n. So that's another way of looking
Uh,
Right, right. Okay.
Professor, I have a general proof for this if you would like me to.
without general proof of what?
Like generally without taking an example ki like at least k distinct elements hone chahiye.
Yeah. Explain.
Yeah. So the cardinal. So let the union of the k columns be ak. Like call it ak. So the cardinality of ak is n minus m times k.
Yeah.
And suppose that we have only like p distinct elements and p is less than k.
Right.
Right. So now let ai be the number of times the ith element comes in the union.
Right.
So we will have like summation ai times ti is equal to m minus n times k,
Yeah.
and the
Ti.
I goes from, yeah, we can call it ti na. तो हमारे जो k elements t elements है, we can call it t1 ti
So this
t1
will be
t2.
like summation ai t. You're saying.
No, प्रोफेसर मैं बोल रहा हूँ कि आर टी डिस्टिंक्ट एलिमेंट्स वी कैन कॉल देम t1 t2 till like tt or something,
Okay.
right? So our summation ai ti is equal to m minus n times k,
Yeah.
and if all the if like since we have ti, like since we have only k elements sum में, तो one of our AIs should be like greater than k, greater than
How?
m minus n, sorry. एक सेकंड प्रोफेसर, ये लास्ट स्टेटमेंट आप खाली एक बार रिफ्रेश करेंगे. सो लेट ए आई बी द नंबर ऑफ टाइम्स आई अकर्स, राइट? सो समेशन ए आई विल बी एम माइनस एन टाइम्स के, तो वो टी आई नहीं आएगा. हाँ, समेशन ए आई इज एम माइनस एन टाइम्स के एंड आई गोज फ्रॉम 1 to t.
Right.
तो
Why
वन
t?
ऑफ आर,
T, there is a confusion.
हाँ, this t, I goes from 1 to t. So we have like t distinct elements. So let ai be the number of times each element occurs, and
Right.
total number of elements is m minus n times k.
Yeah.
So summation of ai from 1 to t is m minus n times k, m minus n times k. So we know that at least one of the ais should be greater than m minus n.
Okay. Yeah. Makes sense.
Yeah, that makes sense.
One of the
So
AIs has to be bigger than m minus n because t is less than k.
yes.
Yeah.
So
So I think,
that
yeah.
would mean this AI has to come at least twice in one of the columns in one of the J's ages.
Right. And that's the contradiction to the previous. ठीक है. Okay. Great. Yeah. It's a little bit, you know, confusing. Anyway, so let's. So I think it's clear, right? I mean, now we can go on. So this was an application of Hall's theorem. Actually, I mean, left to myself, I would have done Hall's theorem towards the end. But so, but Nishad wanted me to show you alternating paths argument. So that's a little clever argument which he never used. So he probably used in his he never used in his talk or never mentioned in his talk. But in any case, so this alternating this blue red business, you know, this alternating path thing is a very clever argument uh, which a lot of people have used to great advantage, and it's a very central kind of approach. So that's good that we are doing it, and you can see that the depth of Hall's theorem is a little bit more than what else we've been doing, because the proof is so clever. Anyway, so back to our graph theory. So let me do some more graph theory. And um, okay, so the first problem in graph theory, the beginning, very beginning, is the bridges. You must have heard of this, of Koenig's work, and this is now called the place is called Kaliningrad. It's somewhere in Russia or something, or East Germany, or somewhere there, somewhere in Germany. And the problem was that there was this town of Königsberg which had, um, so there were several bridges, something like this. These are bridges. These parallel lines are bridges, and you have these uh, sort of islands. Okay, and the problem was that you have to traverse the bridges. So there should be seven, 1, 2, 3, 4, 5, 6, 7, right? So you have to go through the bridges without crossing over again, without recrossing a bridge. So you have to traverse all the bridges, go from A to B to C and D, and you have to come back or not, but you have to sort of go through all the bridges, but you can only traverse the bridges once. That was the problem. Okay. So this was the problem. Traverse all the bridges uh, only once and return. So apparently the villagers tried that a lot in their evening walks and they couldn't manage it. And then they set the problem to Euler, who solved it. And what Euler did was he converted it into a graph. So he called uh, these regions. He made these A, B, C, D as vertices of a graph, and he represented bridges like this as lines between these paths, right? So these are the bridges, and these are the uh, regions. And the problem becomes that you have to go through this graph, you have to draw this graph. So the problem is now draw this graph. Uh, so you cannot lift your pencil, and cannot go over a graph, cannot go over uh, line again, edge again. Okay, so draw this graph without lifting your pencil from paper and without um, uh, without going over a thing again. So, do you want to try a simpler one? So this you can do. You want to try it? Just 2 minutes. Can you do this? So there's no edge here. There's no vertex here. This is just a straight line. Can you do it?
Yes, Professor.
Which one? This one can be done, right?
Left hand side, yeah. Right hand side.
Yes, first one can be
This
done,
cannot be
second
done.
one cannot.
So the idea is very simple. Idea is that so I don't know if you did it, then you probably started from here or here and reached the other point. So if you go like this, no, that doesn't work.
Professor, why does that not work?
So this. Oh, it does work. So like this. So the point,
Basically, the only the first and last one can have an
right?
odd
If
degree, right?
the point which Euler made was that if you're going in, then you have to come out also. So at most, you know, two of the degrees can be odd. So here, this has degree 3, this has degree 3, this is degree 3, this has degree 1, 2, 3, 4, 5. So all are odd degrees. So if you can traverse, then if you have to go in, you have to come out too. So there's something wrong. So this is called an Eulerian path. So we do a definition. So an Eulerian circuit. So I remember, the story about this is that when I was in school, we saw some book where this theorem was explained. So our chemistry teacher was a very big bore. I mean, you know, so so we are we told him that you can't do this on the board. So he got very excited and spent about 40 minutes trying it out. So we wasted one class successfully by asking him to try this. So we showed him some things. Ki this is very easy and we can do it. We are unable to do this, and then he got excited and kept trying and kept doing it. So 40 minutes successfully wasted. Anyway, an Eulerian circuit is a closed trail which contains each edge of the graph. So I'm not counting this as an Eulerian circuit. Okay. So this is not. It starts somewhere and ends somewhere else. That's not allowed. But if I had this guy, then it's fine. So I start somewhere and then I come back here. That's an Eulerian circuit. Okay. And the proposition is, so we want to prove this thing. There is a preliminary proposition. Let G be a graph in which every vertex has an even degree. Then the edge set of G is a disjoint, uh, is an edge disjoint union of cycles. So just a note that when you have a cycle, this is a cycle or a circuit, then the degree is 2. So here degree uh, of each vertex is 2. So this is sort of a simplest possible graph which has a even degree. Everything is even, simplest possible. And then you could have other graphs which are um, you know so if you have something like this is what he wants, right? He doesn't want this guy. Here there is a problem. There is an odd thing. So this is not allowed. This is what he wants. Is an edge disjoint union of. Okay. Okay, so I should mark this one as right.
I said there are only two vertices with odd number, right?
Here, right? Yeah. So the green is not allowed.
Yeah, then that should
The
work.
green is not allowed. Yeah.
That should work then.
It works, but I mean the definition we are taking is for it's a closed trail. Okay, so we'll prove it with these two odd vertices later,
I see.
but first we are doing a simpler case. So the proof is let Q be the number of edges uh, and we prove by induction. We prove by induction on Q. So when Q is equal to um, 2, then we have this kind of situation. So that's okay. It's just one cycle. So suppose the something wrong with this. Has k uh, edges, and the theorem is true for all graphs with q edges where q is less than k. So this is the inductive hypothesis. Okay. So what you do is you take any vertex uh, v0 and you start a walk until some vertex is visited twice. Okay. So let's say this. So what am I doing? I'm saying that I start with some v0, then I go on a walk in our graph, right? So I go to v1, then I go somewhere else, v2, blah blah blah, blah, and I reach here and come back here, here, and suppose over here I come back again, and this point is, let's say, vj, right? Now, so so I start from somewhere, then I go on a walk, and at some point I reach some vertex. And if I've reached this vertex, Vj, so let's say this Vj is. So now what we notice is that this part of the walk from Vj to Vj is a cycle. And what we do is, let's say, call it C. So we delete this this one. We delete this cycle from the graph. And obtain a graph, let's say H, uh, with less than k edges and all vertices of even degree. So what do I mean by remove this guy? So what I mean is that suppose there is something else in the graph, you know, if it's even degree, then there may be two more edges over here, 2 or 4 or whatever. Then I just delete these edges. But if this guy has degree 2, then I just delete these two edges and the vertex. Whatever I get will be a graph which has lesser number of edges, and again all vertices will be of even degree. Okay. So when we delete the cycle, we delete uh, all, so delete means delete all vertices uh, only if uh, delete edges. Let me put it this way: delete all these edges and then remove any isolated vertices. This is what it means. Okay, now by induction, the rest is a uh, disjoint, whatever. The rest, the graph H must be a union of edge disjoint cycles, and we are done. So is this proof clear?
So, Professor, we have to say that there is a cycle only because K is finite, right? There'll always be a cycle because every vertex has at least two edges.
Um, yeah, I mean, um, if I mean, if there is no cycle, then it is also an edge. It's a disjoint union of cycles. So, but yeah, I mean, if it is I mean, if there is no cycle and if it's a tree, it can't have a cycle, right? And yeah, there must be a cycle. So if it's if every did we do so did we do okay,
Oh, Professor.
hang on, did we do this that if T is a tree,
Yeah, then there's at least
it
two
has a
leaves.
pendant vertex?
Yeah,
So I mean, it can't be a tree. Whatever we have is can't be a tree.
correct. Yeah, right.
So it has to have a cycle. Okay, does that answer your question?
Yeah, yeah.
Okay. Yeah, yeah, Ayush, you were saying?
No, I was just going to say the same thing. If there is no cycle, then like at least one of the vertices must have degree like one.
Right, right. Yeah. Okay, so this proof is this is easy, and this makes the other guy very easy actually. So let G be a connected graph. Mm, then G is Eulerian if and only if every vertex has given it. So actually, Euler's theorem is more than what that bridges of Königsberg. Bridges of Königsberg, to say that it doesn't exist is easy. So this side is easy, and this solves the Königsberg bridge problem. So this is, I would say, it's obvious, which we discussed. But this side is what is more complicated, and that requires our theorem. So suppose every vertex has even degree. Okay, then the edges are in a disjoint set of cycles. You take any one cycle, I mean, I want to create a Eulerian path. So you take any one cycle. If all edges are in C1, then we are done. We have, I mean, just traverse C1. So traverse C1. Otherwise, there is um, a vertex V1, say, in C1, and um, um, well, and V2, which is not in C1, such that V1, V2 is an edge say not in C1. Well, this is a little cumbersome. Let me just say, otherwise there is a um, V1 in C1 and V2 not in C1 such that V1, V2 is an edge. Okay, now by our theorem, by previous theorem, V1, V2 must be a part, must be in some cycle, because the graph is a union of edge disjoint cycles, right? So some cycle C2. Okay, so what you do is you insert C2 at V1. So what am I doing? I'm saying that I have a V1, um, then I have this, some cycle here. This was my original cycle, and let's say this point is V2. And no, this, hang on, this is not V2. I mean, I'm starting from somewhere, take any one cycle. Uh, Let this point be V1. And there's an edge V2. And then they are part of some circuit, right? So this is C1 and this is C2. And what I do is I insert this C2. So I have this walk wherever I'm starting from walk. Let's say I'm starting from here. Then I take a walk. Instead of going around here, I'll go around here, come back, and then go around here. That will be my Eulerian, right? So again, if C1 union C2 is equal to the edge set, then we are done. Otherwise, there is some other edge, U1, U2, such that U1 is in one of these, C1 union C2, and U2 is not here. So carry on in this manner to generate Eulerian path. Okay, so well, let me say, instead of generate an Eulerian path, until all the edges are traversed. And that concludes it. So then remark. So in this, I mean, you can see that you can start from anywhere and you can get an Eulerian path. So wherever you are, you can just start anywhere and you will get an Eulerian path, right? You can just go around, find one circuit, then it's touching some other circuit. So you insert that, then maybe there's the third one here, then there's the fourth one here, and so on until the entire graph is done, right? So now coming back to the Königsberg, or Königsberg. If there are exactly two odd vertices in a graph, then um, it can be traversed by starting at one of these vertices and ending at the other. Okay, this is clear. This is clear. So you just add an edge between the two. So is this clear? What we're doing? Let's just try this on this guy. This approach, right? So let's start somewhere. Um, I'll start at this point and I do this. So this part now, this guy is touching some other circuit. Let's see, it goes here and it comes here. That's step one, step two. Now another circuit. Uh, this guy is touching this guy and coming here and then coming back here. So go with this color. This chap goes here. Um, well, this is included. So let's do this and let's do this. And now we're done. So this, I mean, this is an algorithm in some sense for attaching, for creating a Eulerian path, and it works quite well. So anyway, this is an easy exercise. Add a bridge in Königsberg to make traversing all bridges possible. I mean, traversing all bridges, but not necessarily coming back to the same. Okay, any questions so far? Is this okay so far? Any queries?
Professor, for the two odd vertices, is there a way, like a similar algorithm to draw it? Because if you draw all the cycles and you're left with the same two odd vertices, then what happens?
Well, with the odd vertices, what we do is we add a vertex, right? I mean, in this case, we just say that we add a vertex. These are two odd vertices. If we add one guy, then we get the previous graph,
Right, right.
and then you can start from here and do this walk business, and you'll reach the other way. So you'll eventually come back here, and then when you delete it, you'll actually coming back via this point. So you do the rest of the walk.
Okay, okay, yeah, okay, yeah.
So two odd vertices works for Eulerian path, not for cycle, right?
No, not Eulerian path. I mean, Eulerian path means that it comes back to the same point.
So it's a cycle
Yeah, yeah. So an
in some
Eulerian
sense.
circuit is a closed trail, and here we are saying that then it is traversed. So it's almost Eulerian. I mean,
Because if there are two odd vertices and if I start from one odd vertex, like it always, if I start, then I will always be able to go out, but will not be able to come back to the
right,
same.
right. So you have to manage it in some way that you go out from here, but when you come back, you come here, or vice versa. Because when you go out, you can't come back. I mean,
So here we have to ensure that the last cycle we draw has to end at the
right.
other odd vertex.
Last edge should be this guy, one of these guys.
Yeah.
Yeah. I mean, whatever the walk is, you can sort of say, suppose the walk starts from here, right? And then it passes through and it comes here towards the end. Then you can start the walk here and then go from here, right? I mean, that's not a problem. And if you look at uh, our proof, we can take any cycle of C. So you start from anywhere, and it's part of the C. It's some cycle. Okay, so we are sort of going back and forth reverse order, but let me go on to the next topic. This is on trees. I mean, um, normally one begins with the easy graphs, which are the trees and so on. But I went ahead and did bipartite graphs. So we'll have a theorem on one more theorem on bipartite graphs eventually. But I mean, my intent is that we do some basic graph theory, which will not be covered, let's say, in a algorithms course or something like that. So, I mean, I've taught algorithms and I teach some graph algorithms, tree walks, is that, binary trees. So all those things will get covered there in some extent, but I'll do some other things if possible, so that it is less repetition. But some basic knowledge of what trees are, I mean, some basic intuition is required. So anyway, a tree is so these theorems are meant for that. A tree is a connected, simple graph with no circuits, cycles or circuits, and if T is a graph with P vertices, then it has at least two pendant vertices. Pendant means degree 1. So it could have more. I mean, all these are pendant vertices. So these are pendant. So kind of like a minimal tree will have exactly two pendant vertices. Okay, and here's a theorem. Um, let T be a simple graph with P vertices. Um, then the following are equivalent. I mentioned one is a problem. T is a tree. I think I'll just do it. T has P minus 1 edges and no cycles. And 3, T has P minus 1 edges and is connected. Okay, so this is a characterization theorem for trees. So simple, if you recall, simple meant no loops, or parallel edges, right? And most theorems are about simple graphs. I mean, you can modify them if you require more complicated. Okay, so the proof of 1 implies 2. So if p is equal to 1, then this is okay. So p is 1 means it just has one vertex. So it has 0 edges and no cycles. It's okay. Um, suppose it's true for all trees with. So again, proof is by induction. Suppose it is true for all trees with k vertices. Okay. So now you consider a tree T with k plus 1 vertices. Okay. So there must be a pendant edge, pendant vertex. To delete that, to delete that vertex and the edge, get a tree with k vertices, which must have k minus 1 edges by induction. Okay. So what does that mean? I mean, you've got some kind of tree here, and then you have got one edge. This is your tree, and you deleted these guys. You deleted this guy, and you deleted this guy. So where is t? Where does this leave you? So this chap has got k minus 1 edges. Okay. So uh, so t must have k minus 1 plus 1 or k edges. So remember, tree is something with a connected graph with no cycles. So this no cycles business is already there. All we needed to prove was that p minus 1 edges. So is this proof clear? Is this proof fine?
Yes, Professor.
Okay, so now we already have uh, p minus. So we want to prove 2 implies 1, 2 implies 3. We already have p minus 1 edges. We want to show it's connected. So suppose not. Suppose uh, so we wish to he is connected. Suppose not. So let T1, T2, T small t be the connected components. Now T1, T2, all of these guys are um, have no cycles either, because T does not have any cycle. T has no cycles, right? So all these guys T1, T2, T3 are the connected components. So they are connected with no cycles. Uh, so basically they are trees, and therefore by part 2 they have um, whatever, let's say Pi have Pi minus 1 edges. So T has how many edges? T has Pi minus 1 summation edges. So the summation Pi minus T edges, right? But we know that, summation Pi is just P, right? P has connected component. So it has P minus T edges, which should be equal to P minus 1 by part 2. So T is equal to 1. Thus, there is only one connected component. And we're done. Is that clear? So we're using the fact that um, T is a tree, so 1:2 is also somehow being used. Well, I mean, it's kind of like a little circular because it is, yeah, I mean, if it has no cycles, then it is a connect, and it's connected, then it is a graph, whatever. Okay. So 3 implies 1. So suppose T is not a tree. So now we assume that T has P minus 1 edges and is connected, and it is not a tree. If it's not a tree, then it must have a cycle. Right? So if it has a cycle and if I remove one edge, still leads to a connected graph. So I have some graph, and I have a cycle in that graph. I just remove one edge. I remove this edge. You know, I'll still have a connected graph, right? So keep doing this, keep going on until you get a connected graph with no cycles. So you get a tree. Now by part 2, that's a problem with 1 implies 2. Now from 1 implies 2, you have a so now you have a contradiction. Let's say you get a connected curve with less than P minus 1 edges. So this is a contradiction to part 2. or rather 1 implies 2. So, well, this T must not have any cycles. I mean, this the key issue is that this um, P minus 1 business is very critical. I mean, if you have anything other than a tree, this is something which one needs to understand. You have a tree, okay? So you have this is very, if you have v vertices, if you have p vertices and it's connected and so on, then if it's a tree, then it will have p minus 1 edges. And as soon as you have one extra edge, there must be a cycle. Anytime you have p edges. So what is the minimal, if you look at a cycle? So let's see a remark. A cycle on n vertices has n edges, right? So if this is a cycle, so any cycle, this is kind of like a minimal non-tree. And you delete one guy, and you get a tree. So a graph, kind of like a minimal graph with no cycles, this is the best you can do. You have p minus 1 edges. And as soon as you have a cycle, there is a problem. And then, of course, there could be more edges. You know, the maximum number of edges in a simple graph could be p choose 2. So you can have huge number of edges. But this is like kind of the minimal examples. Okay, any questions?
Professor, can you please repeat the last part of the argument for 3 implies 1? Like, what exactly is the contradiction?
Which part?
In the last one, we get a connected graph with no cycles with less than p minus 1 edges. So, what exactly is the contradiction there?
Well, the contradiction is to part 2. So we already proved that if we get a tree, so we get a tree eventually. This is the definition of a tree, but it has less than p minus 1 edges. So if we had a tree, then we would have had p minus 1 edges.
Right, okay, makes sense.
So I mean, it's a little bit, in some sense, it's a very obvious kind of argument. That's why it's so confusing. But it's this minimal business has to be understood very well. That, you know, there's no cycles. It has exactly p minus 1 edges. Okay. So, and if you look at a cycle, it has exactly, so I can write p here, p edges. So exactly p vertices and p, the same number of edges. If you just cut one, then you get sort of like a minimal. So a minimal tree would be something which is an almost cycle, right? And again, if you add an edge, then you're adding a vertex over there. So this number keeps going up. So if you add an edge and a vertex, you're fine. Any other questions?